Hello there, and welcome to our first lecture for multivariable calculus. This is parametric plotting lecture notes, and this is a lot of stuff you hopefully should have picked up throughout the chapter so far, but if not, hopefully we can clarify some things for you. At any point in this video, obviously feel free to pause it, and you can follow along, go back and re-listen to what I was saying. Or if you have any questions on it, you can obviously always email me and let me know if you want further explanation. All right, let's get started. So we're going to graph a couple parametric equations by hand. A couple points here. If you don't know what the graph looks like, make a table. If you do know what the graph looks like, then the table might not be necessary for that. So then plot as many pairs of x and y coordinates as you can over the domain for t, and then once you know what the graph looks like, you can connect the dots. Look for patterns in the functions. Obviously, we know circles and parabolas and lines and ellipses. You should know what those look like by now. But if there's any other patterns that we pick up throughout the chapter as well. And then when you work on your literacy sheets, you can feel free to check your work with Mathable if you want to, or your graphing calculator, just to make sure it's correct before you turn it in. Okay, so let's get started with our first example. It says sketch a graph of x of t equals 3 cosine t and y of t equals sine t. You probably know what that is already. Hopefully we do. We should know that is an ellipse. It's on the horizontal axis, stretched out on the horizontal axis ellipse, and it goes from 0 to 2 pi, so that means it is a full ellipse. So we're not going to need a table of values for this because we know it's going to go 3 out on the x-axis and 1 out on the y-axis. Oh, that's not our ellipse. There's our ellipse. Okay. The second one, sketch a graph of x of t equals 3 minus t and y of t equals 3t as t ranges from 0 to 2. I recognize that as a line. I know it's a line. Unfortunately, I don't know exactly what that line looks like. I don't know where it's at. So for this one, I am going to make a table of values. And you can do a vertical table or a horizontal table. It doesn't really matter. And basically, you just want to make as many values as we possibly can. So from 0 to 2. So if we put 0 in here, we're going to get 3, 0. If we put 1 in here, we're going to get 2, 3. And if we put 2 in here, we're going to get 1, 6. And you can put more points in there. You could put 0.5 or 1.5 in, as many points as you need to get that graph. But this should be sufficient for us to graph here. So when you put 0 in, we're getting 3, 0. Let's plot that point. And put 1 in, we get 2, 3. There's that point. And when we put 2 in, we get 1, 6. So there's that point. And that is our line segment from t equals 0 to 2. Okay, working with derivatives of functions in parametric form. If y equals f of x, then f prime of x. A couple different ways we can write this here. We can write it as y prime of t over x prime of t. Or we can write dy dt over dx dt. Obviously, we know those mean the same thing. So just depends on how you want to write it. To maximize or minimize the x coordinate, you want to set the x derivative equal to 0 or undefined. And same thing for the y coordinate, except this time we are going to use the y derivative. Okay, something you might have picked up on in, I believe it was try it 3, curves and surfaces. A curve is one-dimensional. So it's 1D, we'll call that, and it has one parameter. But meanwhile, a surface is two-dimensional. We'll call it 2D, and it has 2 parameters. We'll start getting a lot more surfaces here very soon. Second page, how do you plot a surface that is parallel to each of these planes? So parallel to the xy plane. If you want parallel to the xy plane, we let z be constant. And then x and y are changing. And parallel to the yz plane, you're going to let x be constant. And then y and z are changing. And the third one there says perpendicular to the z-axis. Well, perpendicular to the z-axis is actually the same as parallel to the xy plane. So again, you're just going to let z be a constant, and then x and y are changing. Okay, tubes and horns. You may have seen this and also in Triad 3. Tubes have a uniform width or radius. Basically, it's just not changing. Okay, the width of the radius doesn't change as you go through it. Horns have a variable width or radius. Excuse my handwriting there. That word is variable. All right, so let's do a couple examples of this here. So first one, describe the parametric equations for a tube consisting of circles of radius 3, perpendicular to and centered on the y-axis. So let's write down those equations here. X of t, y of t, z of t. And because it's perpendicular to the y-axis, that means that it's parallel to the xz plane. All right, so the equation we can come up with for this here is 0t0, and we'll let t range here in a second when we get to that point, plus 3, because the radius here is going to be 3. And then we'll put cosine in the x space here, 0 in the y space, and sine in the z space. All right, and then it doesn't really say how long it has to be, so we can kind of pick how long we want it to be. Let's just use 0 to 4 for t. And then if we want a full tube, we have to make sure that our trig functions complete one cycle here. So we're going to let s range from 0 to 2 pi. That'll give us a full tube. Okay, so what would that look like if we were to plot that? Do the best with your plotting here. Basically, that would look something like this. Something like that, centered on the y-axis. So then it would be parallel to the xz plane. Remember, this is x, y, and z when you're 3D plotting. All right, the next one, we're not going to really get into plotting this too much here because that would be a pretty crazy one to plot here, but we will give parametric equations for a horn centered on that curve. So I'm going to copy this here. X, Y, Z of t. That's going to equal, but we're not going with 0t0 this time because it's not a tube anymore, it's a horn. So we're going to use our p of t equation. So 3t, 4t squared, negative 3 over t. And now since the radius is variable here, we can either put r of t here or we could put t cubed, whatever you want. If you want to put r of t, since r of t is defined, that's fine. Okay, this then is perpendicular to the x-axis, so that means parallel to the yz plane. So that means we're going to keep x as constant here. And we'll put cosine with y and sine with z. Okay, so this time they do tell us what they want t to be here. So obviously we're going to let t be from 0 to 5. And s, once again, if we wanted to complete a full circle, go from 0 to 2 pi. All right, the last one is pretty much the same, except we're changing from a horn to a tube, which is actually going to be a little bit easier. So we're going to use a lot of the same equation from the last one. We're still doing p of t, but now we're doing a tube, so we're going to add 4 instead of adding t cubed. And parallel to the xz plane, which means y is going to remain constant here, so we'll put cosine in the x spot and sine in the z spot. Okay, so then it says the radius 4, we got that covered here. It doesn't tell us the length, so again, we can pick whatever length we want. How about we'll go from 0 to 6. And again, we want a full revolution here. So 0 to 2 pi. And that's it for our first lecture. Obviously, if you have questions, you can ask me during class or email me. And if you have any issues with your try-its, same thing. But hopefully this is all making sense to you, and I will see you back in class soon.